Good morning, Doctor. So, my name is Muhammad Iqbal Arfan bin Kamaluddin, and my matrix number is 251091617. And today, I am presenting Lab 2, Operational Amplifier Configuration using LT-Spice from course EMJ 22204 Analog Electronics. So, I am student 1 and I will focus on inverting, non-inverting and summing amplifier circuit.
Good morning, Doctor. So, my name is Ahmad Nabil Amsyar bin Razik and my matric number is 251061507. And today I will present Lab 2. And I am student 2. I will focus on integrator and differentiator.
So first, let's start with our objective. So our first objective is to understand the basic characteristic of op-amp configuration. And second one is to compare theoretical and simulation results. And the last objective is to study the effect of practical components like bypass resistor, small capacitor and the other on the output. So for our first circuit is inverting amplifier. So in the inverting amplifier circuit, we use R1 equal to 1 kilo ohm, R2 equal to 33 kilo ohm. So giving a theoretical gain of negative 33 when the input was 100 millivolt peak sine wave at 1 kHz, the output was approximately negative 3.3 Vp with perfect inversion and no clipping. However, at 1 Vp input, the output clip at around plus minus 11 volt because the op-amp cannot exceed its supply voltage limit. This clearly shows why it is called an inverting amplifier. 180 degree phase shift. So moving on to the non-inverting configuration. In our circuit, we use R1 equal to 1 kilo ohm, R2 equal to 10 kilo ohm. So the gain is 1 plus 10 divided by 1 equal to 11. With 1 Vp input, we obtain exactly 11 Vp output, perfectly in phase with the input and no distortion. This configuration is very useful when phase preservation is required.
For the integrator, we use Rs equal to 100 kilo ohm and capacitor 0.01 microfarad and Rf equal to 1 million ohm. 1 volt peak square wave at 1 kHz produce a clean triangular output with the correct negative integration slope. The 10 million ohm resistor is crucial. It provides DC feedback to prevent saturation from input offset. Without it, even a few microvolt of offset would cause the output to drift for the rail over the time. Next slide is differentiator. So the differentiator circuit use Cs equal to 0.01 microfarad, Rf equal to 100 kilo ohm and Rs equal to 1 kilo ohm and 100 picofarad compensation capacitor. A triangular input produce sharp positive and negative pulse at the edge, forming an approximately square wave, quite sharp a bit. And the 100 picofarad capacitor limit high frequency gain and prevent the circuit oscillation. Increasing the input amplitude cause the output to clip and distort due to slew rate limitation.
So for our last circuit, it is the summing amplifier. So in the summing amplifier circuit, we use two op-amps, one as a voltage follower for isolation and the second one is inverting summer. So the component we use is R1 equal to 10 kilo ohm, R2 equal to 2 kilo ohm and Rf equal to 10 kilo ohm. Both input 1 Vp at 30 Hz give exactly negative 6 Vp output, confirming Vout equal to negative V1 plus 5 V2. The circuit accurately performed with summation.
End of our presentation. In conclusion, all configuration work as expected in lead-spice simulation. Theoretical calculation method experiment result very closely. The practical component like 10 million ohm in the integrator and 100 picofarad in different theatre prove that essential for stable operation. This let depend on our understanding of op-amp behavior in various analog signal processing application. Thank you. That's our presentation.